Hi, in this video we're going to be discussing section 14.5, which is the chain rule. One could call this the chain rule for multivariable functions because you should already be familiar with the chain rule from Calc 1. So as we often have done, in Calc 1, the situation you would use the chain rule for is the following. You have y equals 3x to the fourth power. Can you do this problem without the chain rule? Yes. But with the chain rule, the general idea is that we want to take the derivative of what we might call the outside function, bring the power down, keep the inside the same, decrease the power by 1, and then multiply by the derivative of what's inside, which is 3x, and the derivative of 3x is 3. Formally, what we can do, you may have seen this, you may have not seen this, is you could let u equal 3x. And so when we have two things going on, we have y equals u to the fourth, and we have u equals 3x. Now, the derivative of u with respect to x is 3, and the derivative of y with respect to u is 4u cubed. And so when we put this all together, what we notice, compare with this equation, what we notice is that dy dx equals dy du times du dx. One way that I'm pretty sure most students end up thinking about this is it's like the du's cancel. Well, that's an easy way to remember the formula. So dy dx is 4u cubed times 3. If that doesn't look familiar enough, if you substitute it one more time, what was u? It was 3x. And so we're back at the beginning. Now, probably you're not thinking of things like this. Once you get good at the chain rule, you might not picture it with a u every single time. But this statement of how we can trace paths down the variables to the dependent variable, from the dependent variable to the independent variable, is the chain rule. Okay, so the idea that we're going to look at composite functions, functions with functions inside of them, a composite function. The chain rule is the idea that we can trace paths. The chain rule says we can, this is not supposed to be graphical, but I'm just saying trace paths from the dependent variable which is y for our example, to an intermediate variable, which is our u, to the independent variable, which is x. And when we do that, we multiply the corresponding derivatives. I know this may sound a little abstruse, but it's, trust me, the same thing you were doing last year. We're just making sure we're a little more clear on the theory here. Notice that even though there's 1, 2, 3 variables, what makes this a one variable calculus, Calc 1 question, a Calc AB question, is that there's only one independent variable. In 3D land, maybe an example to consider while we're saying all the theory, we have a function w that takes in x and y, squares and subtracts them, but we know that x is secretly dependent on some variable t, let's say time, and y is also dependent on that variable t. Okay. So that's the situation we're talking about. We have three functions, so to speak. We have a w function, we have a x function, and we have a y function. But at the end of the day, they are all based on one letter, let's say t. Right? Do we see how that might trickle down? So it's like you would write w as a function of x and y, x is a function of t, y is a function of t. So realistically, we have w is a dependent variable. It's purely dependent. X and y are now intermediate variables. At the end of the day, w is really based on t. The same thing x and y are based on, the the independent variable. Independent variable. Okay. So what we see here, we have kind of two paths now from w to the independent variable t. We have the path through, and this will be very much what we end up drawing, w to x to t, and we have the path from w to y to t. T causes two changes, a change in x and a change in y, which then cause a change in w. I'm going to write all that out. So a change in t causes changes in x and w, in x and y, which cause a change in w. Right? A delta t gives rise to delta x and delta y, which cause a delta w. This should sound familiar. What also should sound familiar from our differentials discussion in the previous section is that a change in w is in some sense the amount x changes w plus the amount y changes w. And the reason we're writing that out is because it's kind of hard to write down until we start thinking about it. How do we get the amount that x changes w? What kind of quantity is that talking about? This should sound very familiar from the differential section. That would be maybe the rate or the slope, rate of change in the x direction of w times delta x, the change in x, the rate of change times the change in x would be the change in w that's caused by x, plus the rate of change in the y direction of w times delta y. And again, the useful thing might be the idea that slope, slope is a change in y over a change in x. So when we want to find the change in the independent variable, when we want to find the change in the dependent variable, we're thinking about slope or rate times delta x. And we're really close now. The idea is that these two rates, what do we mean? What do I mean by rate of change in the x direction of w? What are we talking about when we say things like that? a partial differential, a partial derivative of w dx times delta x plus the partial w partial y delta y. And so if we wanted to find the slope, we wanted to find the slope in w, we might divide by the change in time to get this into a slope. If you're asking me what slope has to do with anything, remember, we're just trying to find, theoretically, the derivative here. That's what the chain rule is for. So we're trying to find the derivative, and the derivative should be based on the change in w divided by the change in time. If we're trying to find the change in w over the change in time, that's why we're going to divide the entire equation by that change in time. So we'll have to divide this term, and we'll have to divide this term. And one last thing, we would do the limit as the change in time approaches 0. That's how we get from a difference quotient to a derivative. From a slope to a derivative, we take the limit as that change is going toward 0. And we'll get that the partial derivative of w with respect to time, with respect to t, equals the partial derivative with respect to x times the partial x partial t plus the partial derivative of w with respect to y times partial y partial t. As I've said, I've never found this particularly challenging to memorize. Most students, once you get used to it, will see that these cancel. And again, you're just adding some sort of change in w with time plus a change in w with time. Don't actually cancel them. The whole idea of this is that this will end up being easier than rewriting this equation for w in terms of our single variable t. But this is the chain rule. That right there is a statement of the chain rule in 2D land. Oops. We're just going to keep that. And that's a proof of this. Now, again, when I was taking this class, I definitely was of the mindset that that formula is easier to remember than this proof. But the proof hopefully shows you why. After listening to this, you should have a good idea of why this formula works, why we're adding up two changes. And the visual from the last video that might help you is we're doing the change in the x component and then the change in the y component. And that's how we can find maybe an estimate for how the slope is going from here to here, right? The total changes. All right. So let's apply that to our actual function. I'm just going to take a second to rewrite this. Oops, sorry. X equals t squared plus 1. Y equals t cubed plus t. The chain rule from here on out is going to be that the partial derivative of w with respect to time is the partial derivative of w with respect to x times the partial derivative of x with respect to t plus the partial derivative of w with respect to y times partial y partial t. Now, a quick word. Most of the time, if you're looking at more careful mathematics, more formal mathematics, it would be written like this. I'm sorry, starting there. This derivative is really based on considering w as a function solely of t at the end of the day. You are realizing that you are not really doing multivariable calculus. You are doing calculus of one variable, just dressed it up. This is a partial because when we're considering this derivative of w with respect to x, we're focused on this equation where w has two inputs. So that should be partial times the normal letter, dx dt, plus, again, a partial w with respect to y, because that kind of w, we're thinking of it as having two letters, one of which is y, times dy dt. Back to normal letters, no partials, because y is a function of just the one variable. Me, personally, I don't mind which one you use. You could use blue, you could use red. Eventually, we're going to go down the path where we're looking at blue exclusively, and that's what I think about it. So it's technically inaccurate to talk about that as a partial derivative because x is not considered to have two variables. It has one variable. Now, maybe that was too much information because at the end of the day, dw dt is, what's dw dx? That's 2x. What's dx dt? That's 2t. Plus, what's dw dy? That's negative 2y. What's dw dy dt? I'm sorry, dy dt. 3t squared plus 1. That's it. Ta-da. Usually we'll leave it like that. We won't worry about converting everything down to one variable. Maybe the hardest part for some people would be getting all that stuff on the paper, right? Just making sure we follow the rules. Now, when we have a problem, we might have to use t to figure out what x, to figure out what y is. But again, usually you're not going to be plugging everything in. You're just going to use the chain rule. It's still the same thing. Take the derivative, multiply by another derivative. I want to say a brief word on tree diagrams. These are usually very helpful in terms of writing the correct derivative rule. So a tree diagram, we're going to put our independent variable usually at the top, w, and we're going to show a dependency of w. Our last function was dependent on both x and y. Okay, this is saying w is dependent on x and y. And then x and y were both dependent on the letter t. They're both dependent on the letter t. So the idea is when I want to calculate dw dt, I would go down the path along x, then x to t. That's one path from w to t. So that would be a partial w, partial x, and then a partial x, partial t, or again, you can be more careful. And then we're going to go down the other path we see to get to the letter t. This might not be as useful here, but please follow this technique. dy, partial w, partial y, times partial y, partial t. And again, those probably aren't partials if we're being super formal. So sorry, I guess I left this off. Intermediate variables. And then our independent variables will be the root of the tree. Okay. I usually seen trees organized top to bottom. If it helps you space out your work. Again, the idea is that W had two inputs. So I'm making a line for each input. These two inputs had one output T. Okay? No big deal. We'll do one more example of the basic stuff. One more example of this basic ideas. So we'll have W equal x squared y minus xy cubed X will be cosine t, y will be e to the t. And maybe we'll have an evaluation. Find dw dt evaluated at when t is 0. Okay. So I'm going to do the whole thing together now. I'm going to make a tree diagram. You don't really need to. It's the same kind of dependency chart we had in the last problem, but just to show you where I'm thinking. When I look at W's equation, I only see X's and Y's. So I'm making a tree that has both X and Y branches. Now, after that, I'm looking at the X equation. Only has T. And the Y only has T. Just one more style of it. Again, it's usually phrased in more of a diamond thing where you would have noticed maybe they're both dependent on T. It's not going to be as easy to do that later on. So again, feel free to get used to doing it. X depends on T, Y depends on T. And either way, we're trying to trace from W all the way down the branches. So when I try to take the derivative of W with respect to time, I'm going to make sure I follow my X branch. My X branch would go dW dx times dx dt plus my Y branch, my dW dy times dy dt. Try this problem out. Pause the video, try it out, see what you get for dW dt. 3, 2, 1. I am getting, for my X contribution, 2xy minus y cubed times negative sine t, the derivative of the cosine. Now the y contribution, x squared minus 3xy squared times, so that's the derivative of w with respect to just y, times the derivative of y with respect to time, which is e to the t. What does it look like to plug in 0? Notice that when I plug in 0, I'm not plugging in 0 for x's and y's. You need to make sure you go through the step that at t equals 0, what does x equal? What does y equal? Well, x equals 1 and y equals 1. This is the example of a function where many students get screwed up just because they forget that when I plug in 0 to some functions, I don't get 0. Make sure you're keeping all that together. So when I evaluate dw dt at t equals 0, you're getting 2 times 1 times 1 minus 1 cubed, negative sine 0, because we're talking about sine of t, plus 1 squared minus 3 times 1 times 1 squared times e to the 0, because now we're back on t. Sine of 0 is 0, so this whole thing is 0, right? That whole thing is gone, and we're just going to be left with e to the 0, 0, so it's 1 minus, e to the 0 is 1, 3 times 1, or negative 2. Easy peasy. If it helps you, you could have noted x equals 1, y equals 1 right here. So this is the basic idea of the chain rule. In the next video, we're going to go over more complicated techniques you can do and extensions of this idea, because having one independent variable is still very much a Calc 1 idea. But this is definitely not a Calc 1 type equation. you have all these partial derivatives. So don't get dispirited. Tune in for the next one, and we'll see how it goes. Thanks for your hard work. See you in the next video.